Okay. Just practicing up a little something old. We're going to get every single one of these equations into slope-intercept form. Because let's face it, you can't be too good at this. This one's pretty easy. Move the x over. Slope's -1, y-intercept's 4. Also an easy one. Move the x over. Y equals 2x plus 10. Slope's 2, y-intercept's 10. Another easy one. Slope's 3, y-intercept's 12. All right, this one we got to do some work on. Yay! Those were pretty darn easy. Excuse me. Okay, so we've got a -2 over a -5. That's a positive 2/5 in front of the x. -1 over -5 is positive 1/5. And yeah, you wouldn't want to graph that, but you could. I mean, it's got a y-intercept of a 5th. Rise 2, run 5. Then this one, we'll move the x over, makes -6x. If the opposite of y is -6x plus 11, then the regular of y is 6x minus 11. And, ooh, here's an interesting, oh, no, I was going to say, it could be interesting. It's not. It's the y still there by itself. So, slope of 2/5, y-intercept -2. Okay, the reason we're remembering all that is because we're going to focus in. We've mentioned them, but we haven't focused in on just the special solutions. We haven't really, like they haven't been on something that you would have gotten graded for. But there's 3 things. Hang on. Sorry. There's 3 things that can happen when you draw 2 lines. They either cross in just one spot. If that happens, the solution is an ordered pair. Okay. They can not cross at all, and then there isn't a solution. Or you could have one line on top of the other, and then the solution is every single point where they intersect, which is every single point on the line. So remember, this is how many solutions. We write our actual solution this way. It's not just any point that works. It's all the points on that line. Okay? So we're just going to do a few of those and just make sure you get the hang of it. So it says solve using each of the 3 methods and by inspection. Okay, so here's, oops, they're too close to the top. It won't let me write on it. So here's the first line. I'll do it in green. And I'm going to do all 3 methods. Oh, I guess I should keep the green. Okay, so first, here's the solution by graphing. We've got a y-intercept of 1. We're going to rise 2, run 1. Okay, got that line. We'll do the other line in a different color. Let's go gray. Y-intercept of -5. 1, 2, 3, 4, 5. Rise 2, run 2. You can hunt for that intersection all day. You're never going to find it because those 2 lines have the same slope but different y-intercepts, which makes them parallel. So there is no solution. Okay. The by inspection, there's a couple ways we could do that. Is that you can just look at the equations of the line once they're in slope-intercept form and notice that they have the same slope, different y-intercepts. Therefore, they are parallel lines. They never cross, and therefore there's no solution. Okay, so that's one way of doing it by inspection. If we wanted to do by substitution, it says y is 2x plus 1. We'll plug that in where y goes. And then if I get my x's on one side, numbers on the other, I get 0 equals -6. Not true. And with a system, that works out to be just like it was when it was just a regular equation. Variables disappeared. you ended up with a false statement. That means there's no solution. Then if we wanted to do by elimination, you probably want to move it around just to feel more comfortable. So like, say you're looking at that top equation right there. If you brought the x's back to the left, it would look like that. On the same second equation, bring the x's back to the left. It looks like that. Okay, now here's another way of doing it by inspection. If you just looked at that, it's saying negative 2x plus y is equal to 1 and negative 5 at the same time. Well, that's impossible. You know, to negative 2 times a number plus a different number, and possibly it could be the same number, can't equal two different things at the same time. Like, that's just not going to happen. So that's another way of figuring out that this thing had no solution. But if we were going to do elimination, you'd probably want to multiply one of these by negative 1. And then when you add them up, you get 0 over here and 6 over there. Again, not true, which would lead us to saying it's no solution. So the whole point of this page is for you just to realize, hey, there's lots of ways of knowing it's no solution. You don't need to do them all. You just need to know no solution. Like, just figure out. There's not an answer. There's no point, or there's no ordered pair that makes both those equations true. So, in whatever way you want to. Now, if it tells you how to do it a certain way, then yeah, do it that way. And this is just mostly for standardized tests. I don't think we're going to ever ask you this on a test or quiz in here, but you say when you have a system that doesn't have a solution, we said that's an inconsistent system. Oh gosh, I got all kinds of stuff on my glasses. Ah, they're filthy. What in the world? I can't even see through them. It's pretty bad. All right, so this one, same thing. If we're going to solve this system, let's do it by graphing first. So I'm going to take each equation, rearrange them. Oh, there's both lines. 2x plus 3, rise 2, run 1. So I guess if I did both two different colors, you can see them. It's the same line. So every single point on that line is a solution. So my solution to this system, it's all the ordered pairs that lie on the line 2x, y equals 2x plus 3. That implies that there are infinitely many solutions. And just doing it by inspection, that just means, oh, I just looked at it. Oh, same line. You just notice, oh, it's the same line. 2x plus 3 and 2x plus 3 equaling the same thing. It's always, you're good, you know. If you did this by substitution, we'll see what happens. I would take that top equation, plug that into the second one. I get 6 equals 6. The variables disappeared. You know, back in chapter 1, when that happened, we'd say it was any real number. It's not any real number. It's because it's not just a number. It's an ordered pair. It's just ordered pairs on that line. If you did it with elimination, let's write down the system again. So maybe you multiply the top times negative 2. up. 0 equals 0. That's a true statement. The variable, oh, it looks kind of like a 6, sorry. The variable's disappeared. Again, if it was an equation, we'd say it's all real numbers. It's not an equation, it's a system. We're hunting for the ordered pairs that make them both true. It's all the ordered pairs on that line. And if we have a system where there's infinitely many solutions all on the one line, we call that a consistent dependent system because one line depends on the other. Another way you can do it by inspection is this. You could take that second equation, like the first equation, if you just left it like it was. If you take the second equation, notice that those will all divide by 2. You'd notice they're the exact same thing that way too. Okay. And then over here, we're just practicing up whatever could happen. Solve the system. And, well, here's, I'm going to do that A. What if I divide everything by 2? X plus y equals 3. X plus y equals 3. That's going to be the same line when I graph it. It says the exact same thing. That line that I graph would be y equals negative x plus 3. So the solution to this is all the points on that line. And I didn't have to draw it. This one, let's say I divided everything right here by 2 and then moved it around. Look at that versus that. Same slope, different y-intercepts. Those are parallel lines. Oops, I guess they both run downhill because it's a negative slope. They are never going to cross. This has no solution. Okay. This one, well, let's just say we multiply the top one times negative 1. This one's going to have a solution. Now I plug that back in. I plugged it into the top one. Solution of that is 2, 1. This one, if I move this around, now look at those 2 lines. Same slope, different y-intercepts. Those are parallel lines. There is no solution. So now you're kind of given some, for the most part, some leeway how to solve your systems. We know lots of different ways. You just pick what you think is going to work the best and you do it.